Okay, good morning, guys. Please go through the syllabus, Unit 1. What are the contents in Unit 1, Transmission Lines, Part 1? First topic is the types of transmission line. Okay, here I'm not showing, but I think you may have a syllabus, right? See here, page. Now see here. Okay, what are the contents present in Unit 1? Already I told you this electromagnetic waves and transmission line is the and that subject contains two parts. First part is electromagnetic wave theory and static fields, magnetic fields, and combination as a electromagnetic wave and Maxwell's equations. And those are the contents available in part 1. And part 2 is the transmission line. Again, that part 2 is split into two parts, right? That part 2 is split into two parts as a transmission lines 1 and 2, but the transmission lines 1 is the only small definitions only. Okay, only small definitions. Okay, but from the second unit onwards, you have some typical content. In that part 1, uh, what you learn, what is meant by transmission line, basic definition. Later, what are the different types of transmission lines? Okay, coaxial cable, twin lead, metallic cable, okay, coaxial cable, okay, two lead, okay, or twin lead, okay. What is such type of transmission line? I mean, metallic cables are studied, right? Next, what are the different parameters of the transmission line? Attenuation, okay. So what are the parameters? I mean, primary constants, secondary constants, okay. In that, all LGC parameters, gamma and Z naught parameters, okay, and the equivalent circuit of the transmission line, okay, T and phi equivalents, okay, it's nothing, okay. Whatever you see earlier, the equivalent circuit of the transmission line, basically that is the phi type, okay. Okay, okay, here, okay, I show you what is the difference between T and phi equivalent circuits, okay. It's very easy, okay. And next topic is the transmission line equations. Okay, what are the transmission line equations? Gamma into Vz equal to R plus j omega L into Iz is the first transmission line equation, and second transmission line equation gamma into Iz equal to G plus j omega C into Vz, right? That is the transmission line equations. And what are the primary and secondary constants? R, L, G, C are called the primary constants. Gamma and Z naught are the secondary constants. Okay, and this is also you learned the expression for characteristic impedance in terms of primary and secondary constants. What is the expression for characteristic impedance? The characteristic impedance is permanent notation is Z naught. That Z naught equal to square root of R plus j omega L by G plus j omega C. That is the term you learned. And propagation constant is also defined. Okay, how? Okay, from the wave equations, simply multiplying that equation 1 and 2. Okay, and please go through the slides. uh, Propagation constant notation is the gamma. So gamma equal to square root of R plus j omega L into G plus j omega C. Okay, whereas characteristic impedance is the ratio, whereas propagation constant is the multiplication factor. Okay, that is the two terms you learned. And next, phase and group velocities. What is the expression for phase velocity? Phase velocity. Phase velocity is nothing but V sub x p equal to velocity equal distance by time, right? Distance is nothing but lambda, time is nothing but 1 by frequency. Okay, that is simply f lambda or omega by beta. That is the alternate form already, you know. Phase velocity is simply defined as omega by beta. Okay, where omega is the frequency in radians per second, and beta is the phase constant or simply wave number. Okay, that is also you see. And group velocity is nothing but, of course, the phase velocity, but with a differential manner. So d omega by d beta is nothing but a group velocity. That is also learned. Next, infinite line, lossless line, distortionless line, and related problems. Even okay, only the transmission line part one is definitions. Okay, infinite line. Okay, and when the given transmission line acts as infinite line, when the given transmission line acts as infinite line, and when the transmission line is terminated with a characteristic impedance Z naught, when the line is terminated, and I mean enclosing at the second end with characteristic impedance, that line acts as a infinite line. Okay, remember that point. And okay, again, we will go through that concepts also in the later section. And lossless line. Okay, when the line is said to be lossless line, when the line is said to be lossless, there is no loss, means there is no resistance or dielectric conductance. Okay, what it means, in the primary constants r equal to 0, g equal to 0, then it is said to be lossless line. R equal to 0, g equal to 0, that is the condition, that is the condition to obtain the lossless line. Okay, I will show you everything, don't worry about it. Okay, that is the lossless line. And next, a distortionless line. What is meant by distortionless line? What is the condition for the distortionless line? The condition for the distortionless line is R by L equal to G by C, or LG company equal to RC. That is the distortionless line. Okay, the same is substituted in the characteristic impedance and propagation constant expression. Okay, we get alternate forms of the characteristic impedance and propagation constants. Okay, and these are the terms we learn from the concept one. Okay, okay, so go to the regular topic. Must see here, characteristic impedance, already you know, Z not equal to square root of r plus j omega by g plus j omega c according to the lossless condition. But remember, okay, take the schematic. What is meant by transmission line? What are the different types of transmission lines? What are the different conditions imposed on the transmission line? What are the different conditions we imposed on the transmission line? Basically, transmission line is the transmission line. It doesn't contain any losses or distortion. That is the basic transmission line. That is the case one. And case two, when we consider that a transmission line with some losses, that is called lossy transmission lines. Okay, that is the case two. And case three, distortionless transmission line. Okay, did you get the schematic? Okay, what I told you now. Here, transmission lines are classified into three types. Okay, and according to our assumption, basic transmission lines with no loss, transmission lines with no distortion. What is the condition for no loss? R equal to 0, G equal to 0 is the lossless. Okay, and if it is the lossy, definitely there exists some R component and G component. And if by default, this is the characteristic impedance, right? It contains R, L, G, C terms. But when we consider the same expression for the lossless, R equal to 0, G equal to 0, just I am putting R equal to 0, G equal to 0. Then we get omega root over L by C. Okay, that is the lossless condition. And third case, R by L equal to G by C. Just I am replacing R by L equal to G by C. And from that relation, if we replace these components, R by L equal to G by C, simply from that what is meant by L and what is meant by R. Okay, from that expression, if we replace these terms with that condition, then that is called a distortionless condition. Okay, this is called lossy, this is called lossless, this is called distortionless. Three conditions. Okay, that the entire transmission lines units going through these three components only. Okay, remember that point. Then you are getting okay, backbone of the transmission lines. Okay, already you know what is minimum velocity vector in yesterday's class, right? This is also wave propagation. I mean propagation constant. Okay, these are all not required. Okay, what are the different losses occurred? Okay, what are the different losses occurred? What are the different losses occurred in transmission line? What are the different possible losses? Okay, with respect to frequency, see here, conductor losses increases with frequency, and whenever the frequency increases, losses also increases. But how, we'll see in the concept of electromagnetic waves. Okay, and whenever the frequency increases, because of the problem called skin effect. Okay, okay, here I mentioned increases with the frequency due to the skin effect. Skin effect means from the center of the conductor, conductance decreases. From the center of the conductor, conductance decreases. And because of that high frequency, okay, all the conduction takes place on the surfaces only. Okay, because of that reason, because of okay, that problem is called a skin effect. Okay, that is called a conductor losses. Next, dielectric heating losses. And basically, dielectric is the non-conducting, but because of the heating, there is a possibility of existence of conductance. Okay, because of that, there exists some losses. That is called a dielectric heating losses or temperature losses. Okay, also increases with the frequency. Next one is the radiation losses. Radiation losses means already I told you. Okay, what is the difference between network theory and electromagnetic wave? Electromagnetic waves concept. Okay, why the losses are very low in low frequency, and why they are increases with increase in frequency. Okay, that is the radiation losses. Okay, of course that radiation losses are not significant with good quality coax properly installed. I mean, and proper installation on the surface is there, then there is a possibility of reducing the radiation losses. That's why the coaxial cable also having okay, very thick insulating material. Okay, and when we observe the coaxial cable of TV, okay, it contains a two copper wires, inner conductor and outer conductor. Inner conductor also having some outer insulator, and outer conductor also having outer insulator. Okay, white and black color. Okay, observe. Okay, if your system, if your TV is connected with a coaxial cable. Okay, and that radiation losses increases with open wire cable, and if the conductor doesn't having any proper insulator on the surface. At the same time, the coaxial cable in general available with a length of okay, few meters, right? Few meters, but I want to extend that length. Definitely I have to couple one coaxial cable with another coaxial cable. Okay, if the coupling is not proper, if the coupling is not proper, if the coupling is not proper, then definitely there exists. And when we connected it to water pipes, when we connected it to water pipes, okay, and when we are properly joined together, then definitely there is no leakage from that coupling. Okay, if they are not properly coupled, okay, and the physically available water coupling is somewhat difficult, okay, then the coupling of two axial cables, okay, with the information or data which is flowing through that wire is not visible. But how it is possible to control that coupling? I mean, how effectively we are performing that coupling between the two coaxial cables? How it is possible? Okay, of course, but okay, some of the techniques are there for the coupling of two axial cables, but if the coupling is not properly performed, then there is a possibility of getting more and more losses. Okay, that those losses are called coupling losses. Because of that coupling, if there exist any losses, they are called coupling losses. And okay, last one is the corona. Okay, actually, uh, here the corona is nothing but mm, of course here and how they mentioned I don't know. Okay, but remember this point. Okay, I will tell you again. See here, transmission line losses with respect to frequency. See here, signal strength decreases with respect to increase in frequency. See here, and whenever the frequency increases, okay, whenever the frequency increases, okay, signal amplitude decreases, right? Okay, see here, frequency increases and okay, signal amplitude decreases. Okay, and this is the effect of frequency on the transmission lines. See here, attenuation per every 100 feet. And attenuation means the radiations offered by that transmission line, right? Radiations offered by that transmission line. Okay, and whenever the length of the transmission line increases, whenever the length of the transmission line increases, okay, the distributed parameter components or LGC also increases. And whenever the RLGC components increases, and that is resistance increases, the attenuation constant, I mean attenuation is also increases because of the attenuation, signal strength decreases. Okay, that is the okay, semi-log representation of the attenuation for 100 feet. Okay, that is a case study. Step applied to infinite line. Okay, step applied to infinite line means, and when we consider a transmission line of infinite length, and when we consider the transmission line of infinite length, okay, for that infinite length transmission line, when one step signal is applied, okay, so step signal is applied means one step, okay, which is having a finite amplitude and finite time period, and that is the bounded input. And when a bounded input is applied to that infinite transmission line, what is its reaction? See here, that voltage step will be propagated down line. Okay, energy is stored in the capacitance and inductance. Energy from source appears to be dissipated by a line, but it is really stored. Okay, if a line is infinitely long, the step never reaches the end. Okay, voltage and current have a definite and finite values. See here, and these are the points observed from that. Whenever the step is applied to, see here, okay, and whenever one step is applied to infinite line, this is the infinite line, and this is the never ending line. Okay, and whenever this voltage is applied, the applied signal is propagated through this transmission line. Okay, that is the point one. Okay, at the same time, when we consider this transmission line is neither lossless line nor distortionless line, okay, it means it is considered as a general lossy infinite line. That's why the transmission line itself contains primary and secondary constants, right? Primary constants and I mean or LGC parameters. Okay, what exactly it means? It contains some resistance, conductance, capacitance, and inductance. But capacitance and inductance are the energy storage elements, right? Okay, but when we applying this step voltage, that step voltage is stored by that capacitance and inductance of a distributed parameters of this transmission line. That is the second point. And third point, energy from the source appears to be dissipated by a line, but it is really but is really stored. And actually, whenever the signal is applied here, okay, actually the purpose of the transmission line is to okay, carry that signal from source end to destination end. But where the destination end is located, basically this is the infinite line, right? This the line is said to be infinite, then that load is connected at infinite point, and actually that I don't know, we don't know where that load is connected. That's why the signal applied at the source end never reaches the destination end or never reaches to the load, but the signal must lie in the transmission line. But where exactly that signal lies in the transmission line? Is it dissipated completely to zero? No, but of course, okay, it seems like a dissipated, but that is stored in okay distributed inductance and capacitance values of the transmission line. Okay, that is the point three. Energy from the source appears to be dissipated by line, but is really stored. Okay, if a line is infinitely long, and if the line is infinitely long, the step never reaches the end. Why? Because the destination, we don't know where the destination or load end is connected. Okay, that's why that never reaches the end. And next point is voltage and current have definite and infinite values. Of course, because of that step voltage, definitely there exists some current, but that current is finite because of that step voltage. Okay, okay. That is the step applied infinite line. What are the reactions performed by the transmission line? Okay. Now come to the main concept. Okay, reflection of voltage step. Reflection of voltage step. Okay, and when the line is said to be infinite, when the line is said to be infinite means, okay, that is having a infinite length. Okay, and when the signal is applied at the source end, okay, uh, the signal is propagating towards infinite, right? That's why there is no reflections takes place. Okay, okay, that is the step one here. Infinite line means, okay, the signal applied at the source end is flowing through the transmission line infinitely, okay, or never ending. That is the infinite line. Because of that, there is no reflection takes place in the infinite line. Okay, remember that point. Okay, that is the first point. And second point, if the line is said to be finite line, which is having a finite length, and where the load end is connected is known. Okay, see here, finite line with load impedance ZL equal to Z naught. Finite line with load impedance, and if the line is finite and which is having a finite length, and the load impedance is ZL, and if the load is, I mean, destination end is terminated with ZL. Destination end is terminated with ZL. Okay. For suppose if the destination end is terminated with ZL, but the termination end which is equivalent to the line characteristic impedance Z naught. Okay, what is the characteristic impedance of that line? That characteristic impedance of the line depends upon primary and second primary constants, right? Or LGC parameters. From that we calculate Z naught equal to square root of R plus J omega L by G plus J omega C. That is the Z naught. If its value is equivalent to that load impedance ZL, then there is no possibility of reflection takes place. Okay, and exactly matching. What is the maximum power transfer theorem? According to the maximum power transfer theorem, okay, source, source resistance equal to load resistance means RS equal to RL, right? Or when we consider the impedance, source impedance equal to complex conjugate of the load impedance, right? And when those two are matched, maximum power transfer from whatever it's applied at the source, definitely uh, it's received by that load, that without any reflections or without any loss. Okay. Similarly, here, if the transmission line is terminated with load impedance ZL, but that load impedance value is equivalent to that entire transmission line characteristic impedance Z naught. And if for suppose those two are equal, and if for suppose this is some 50 ohms, that is ZL is also, when we terminated with ZL is also 50 ohms, and both are equal according to the maximum power transfer theorem, maximum power transfer without any loss. Similarly, here when ZL equal to Z naught, there is no possibility of reflection takes place, and without any, I mean, there is no loss, okay, because of that matching impedances. Okay, that's why here no reflection takes place. The load looks into the source like an extension of the line, and it seems like an infinite line. Okay, and third point, voltage and currents are compatible. Okay, and voltage and currents are compatible means okay, and there is no possibility of reflection takes place because of that voltage and current mismatch. Okay, see here, and line impedance Z equal to square root of L by C. Okay, or Z not equal to square root of L by C. Of course, Z not equal to ZL here. That's why Z not equal to ZL equal to Z equal to square root of L by C. Okay, see here, and next point is finite line with load impedance ZL not equal to Z naught. And here ZL terminated load impedance is quite different from characteristic impedance of the line. Load impedance of the transmission line is quite different from characteristic impedance of the line. Okay, that is infinite line with load impedance ZL not equal to Z naught. Okay, At that time, that transmissional line never acts as an infinite line. Okay, because of the mismatch. Is it holds good for the maximum power transfer theorem? No. Okay, ZL equal to Z naught, then it is the maximum transfer theorem. ZL not equal to Z naught here. That's why that line never acts as a definite line, and it is always the finite line. Okay, and whenever we apply that step signal to that finite line with mismatched load and characteristic impedances, definitely there exists a possibility of reflections. Okay, and, when two pipes having the same size, two pipes are having the same size, those two pipes are coupled to each other. Okay, is there any possibility of uh, uh, I mean, spillover existed that spillover existed at that second pipe, and because of the reducer size? No. Okay. For suppose I'm taking a 1 inch pipe, I'm coupling 1 inch pipe with another 1 inch pipe. Okay, there is no problem, and there is a possibility of smooth going of that water, right? But when I'm coupling that 1 inch pipe with the half-inch pipe, okay, definitely the pressure level increases at that half-inch pipe. Here also the same. Okay, see here, and because of that, some reflections occurred. Okay, finite line with load impedance ZL not equal to Z naught. Okay, and whenever that step, okay, that step voltage is applied at that finite line, but because of that mismatched load and characteristic impedances, definitely there exists a reflections. Okay, that's why that next concept is reflection coefficients, reflection parameters. Okay, reflections and standing waves. Okay, so the next concept is reflection of pulses from the transmission line when that transmission line is short circuited and when the transmission line is terminated with ZL equal to Z naught and ZL not equal to Z naught. Okay, and these are the cases. These are the three possible cases we have to consider for the transmission lines. Okay, so I want to stop here because we have a faculty meeting with our HOD sir.